So, welcome to lecture number 3 of this module 4. In previous 2 lectures of this module, we discussed the various overvoltage, various faults in the whole system, as well as we saw the mal-operation of converter circuit itself. Today I am going to discuss the protection schemes. Those are used for the various faults. Now the protection, as its name, we require some desirable features for the protection schemes, and these are the 5 important desirable feature or characteristic of any protection scheme or system. First, it should be selective, it should be discriminative, it should be reliable, and it should have a fast speed, and there should be some backup protection. Here the selective means where the protection system is designed for a particular zone or particular apparatus, then it should only operate if there is some problem in that zone or that apparatus. So it should be selective. If the disturbance outside that zone, it should not operate, even though there is, let's suppose, I can say here simple, let's suppose this is your bus and this is a line in AC system, this is your protection scheme, and if this relay or protection scheme is designed to have the fault only in this line, so it should only operate here in this zone, so it is called selective. Means whatever the disturbance here on outside of this zone, if it is operating, then it is not selective. So it should select for which it is designed. So the selective zone, it is called, the relay should be selective. Another is the discriminative. Discriminative means there is a 2 type. One is for example, let's suppose there is some fault here. The current in this line will increase. There is also possibility that due to the overloading there is no fault, the current is increased. So the discrimination of the relay, that it should clearly discriminate where there is a fault or there is a overload. So a relay should discriminate between the faulty condition and the healthy condition. Means in healthy condition there may be there may be disturbance, maybe let's suppose the current is higher. So your overcurrent relay should not operate for the overloading, only it should operate once the fault is there. So the discrimination or relay should clearly discriminate whether there is a fault or it is not fault. Reliability is a concern that we should design our scheme in such a way that the relay should operate for which it is designed to. If it is designed for a fault here for the current, then it should operate for the current. If it is designed for overvoltage somewhere here, it should operate in the overvoltage mode. So the reliability basically related to the design, and it should operate successfully whenever there is some fault or some problem is occurring in the particular zone. So we can say relay is reliable. Our protection scheme, because protection scheme consists of your relay, which is a sensing device, and then it is your circuit breaker in AC system. It should open and operate it. If there is a fault here, it should open here both end, and then fault can be cleared. So this is, including these 2, it is called your protective scheme. So I am just talking in a general way right now, and then we will move to our HVDC system and we will see. So your relay scheme, means your protective scheme should be reliable, that it should operate whenever it is desired to. It should not operate in the undesirable conditions. Then we can say our relay is reliable. The 4th criteria or characteristic is the speed. It is very ambiguous that always we say that if there is any disturbance, our relay or our protective scheme must isolate the faulty section as early as possible. So we require our protection scheme should be fast enough to isolate the faulty section, so that there should not be any damage of apparatus or any other device in that job. But now the question arises, how fast? If your relay is operating very fast, what happens? There are some conditions, there is a very minor transients are there and it is basically die out, and if your relay is operating, so what happens is they keep on operating, which we never wanted. So it should be fast but not be extremely fast, because extremely fast sometimes, even though it is not necessary to operate, if it is operating, if it is very fast, even the small disturbance, or maybe for example, let's suppose there is some transient is coming and it is spurious signal is coming and it is dying out. We don't want our relay should operate, because it is not going to damage the healthy system at all, then it should not operate. So we want our relay scheme, our protection scheme should be fast enough, but not be very extremely fast. No doubt it should not be slow. If it is slow, then what will happen? Let's, for example, if there is a fault here, huge current will flow and this line or your apparatus which is connected here may damage. Another is we should have the backup protection. Backup, as it means that if the primary fails, then backup should take over, because this is a relay which is having your, maybe it is a digital relay, it may have so many sensing devices, and there is a possibility that it may fail. So you can imagine if there is a fault and this relay is not operating to this circuit breaker, what will happen? This is a huge current will be flowing and this your apparatus may damage. Here may be transformer, another device are there and it may damage at all. So we want, if it fails, then after certain time a backup should be there, because this is a very expensive system. You know, the fault of, if it is a persisting, your system may lose the stability. So we want that if it is a designated for the particular section here to operate, it should operate. In case there is some problem, if relay is not operating, then there should be a backup relay which should operate here, and then we can isolate. But that backup relay should operate only after if it is not operating. So there is some time lag. So it will see when the current is exceeding due to the fault, then it will wait for certain maybe 0.5 seconds, and then it will operate and it will isolate our that. So we should always design our protection scheme that there should be one backup. If the primary fails, backup should be there to have the complete reliability and security of the system. So these 5 are our desirable characteristic of the protection scheme. This is the basis. This is used either it is your AC system or it is a DC system, or even for any other purpose if you are having some protection. Even though, you know, this is also, you can see this is can be also applicable for a protection of some area due to the thicker security threat and other things. All we require this, it should be selective, the dedicated work of any person should be discriminating, whether really some terrorist attack etc. Means this is a general, I can say it is applicable to your electrical system, whether it's AC or DC, it is true everywhere. So now we have to come back to our main here. Now let us see in the AC system, basically it can be broadly classified. We are having the 2 type of problem in AC system, that is, one is your overvoltage and other is your overcurrent. Means all the protection schemes basically based on either overvoltage or overcurrent. We never operate our system with the undervoltage and the undercurrent, because undercurrent, if there is no load here, the current will be 0. I don't want to open this line. Sometimes we also try to see that, for example, let's suppose you can see in where the current is 0, but still we want the protection. You know, we have the 2 types of faults in the AC system. What are those? Is open circuit or short circuit. If open circuit means this, let's suppose this is a broken. Current is 0, your overcurrent will not operate, your overvoltage will not operate, under voltage will not operate. But how to know this? And that's it is, you know, if potential is here, huge potential, and it is falling on the ground, then this is creating problem. So normally this possibility is very rare, very rare, because opening of a wire in between, it is very rare. As I said in the last term, it is normally broken especially at the joints, and joints normally made near to the poles. So if this is there, so normally it is, now how to know it? It is basically this, we may go for the distance relay and some other relay. We can see that here the current is 0 or some charging etc. is there. Based on that we can calculate some other relays are there, but not a normal conventional relay will not operate. So this is very rare, and it is not to have protection for all these type of sections for open circuit. So only we design our protection scheme especially for the short circuit. And short circuit, once it is happening, means there is a huge current. And also there is a, if short circuit is happening, suppose line to ground fault is there, so unhealthy lines may the voltage will be higher. So the over voltage and the under voltage we never go for. So over voltage and over current protections are used in AC system. So the causes of over current here, over voltage, you know, if it is a lightning is coming on this system, then there's huge energy because steep current is falling on this your wire. So this is a traveling on the conductor and huge voltage is generated. So that is called lightning voltage, overvoltage. Another overvoltage is due to the switching, because if you are opening and closing this, there is a voltage generated on this circuit breaker, because there is a energy exchange between inductor and capacitance. So this switching overvoltage and your lightning overvoltage are the two concerns. And another, even though due to the normal operation, if there is a line to ground fault is there, other phases voltage may go high. So we'll come back and we'll see here now then how to protect it in AC system. If it is a lightning surges which is causing your overvoltage, then we use the overhead ground wire on top of the wires, because you see your substation as well as most of the substation, I can say ESB, they are exposed to air in the environment, so there is a possibility of the falling the lightning strokes. But that's why we have the so many, you find there is so many spokes, there is so many the lightning arresters are there, so that it can get the ground path without affecting your apparatus. But the wires which is flowing, going between the two substations, it is exposed to air again, and then we put some ground wires on top of that, that if there is any lightning stroke is there, so that it can protect your line and finally it go to the towers and finally discharge it. But still it is not possible to protect completely, then we go for other protections as well. So we use here overhead wires for this. Normally even those substations are also protected with the some overhead wire. Sometimes we put the arresters so that we can provide the ground path. We also use the protective gaps. Protective gaps we also use in the DC system. What it meaning here, this is your, I can say this is here and this is a grounded. This is the gap, a simple very small gap. Now if the voltage here rises, what happens? The air which is here will get ionized, and once it is ionized, then it will follow, this will be follow a conducting path, and this here it is a grounded. So it's a plain gap, we call it the gap here, and normally it is used here. But this is a very cheap and a very conventional approach to protect the overvoltage here. It has a problem, you know, this is a dead short circuit. When it will be deionized, it is very difficult to say. So it is some sort of a fault here, which is no doubt for that it is protecting, but you require that it should go off when voltage is normal. But normal voltage is also very high. Once it is ionized and it is falling here the path, this will be always ionized and it will follow the conductor. So it is a very difficult sometimes to have this very proper protection. So what we use, we go for very high voltages if it is rising. So we try to increase the gap. If the voltage is normal, then it should be deionized so that it can be cleared. Another scheme here, we use the lightning arresters itself. Lightning arresters are again the following in the similar concept, but here this is normally we denote like this. Here we use the non-linear resistors. We use the stacks of resistors so that when voltage rises, its characteristic changes and it provides the ground path, and once it is a normal voltage, it provides the open circuit. So its resistance value of this here it changes, that is called lightning arresters. So very widely we use the lightning arresters, but it is expensive, than here it is a very simple one. So very high voltage in the near to here we put the protective gaps. So this is basically the over voltage protection scheme in the AC system. Now if you are going for the overcurrent protection, what we do for the overcurrent, if the current is exceeding, then we have to open the circuit breaker. It's very common. The fuse is there, huge current will be flowing, then due to the I square R, this will be blown up and fuse will be open. So we can use the fuses, we can use circuit breakers, we can use relay some sort of, and you can basically the circuit breaker is operated based on the relay operation. So we use the relay circuit and then circuit breaker is open. We sometimes use the current limiting reactors also to reduce the overcurrent, because if rate of rise current is very high, so we can use the limiting reactors that can safeguard, means current will rise but it will be limited by this reactor value, and then we can protect our system. Now come to this here, in the HVDC system. HVDC system, again you can see we are having the two types of here, the overvoltage protection we require, and we are having the overcurrent protection. So the overcurrent protection, overvoltage protection is similar to the AC type with some small differences. AC side is same, but the DC side overvoltage if happening, then we use the different schemes for overvoltage protection. We'll see. Overcurrent protection, here we can use overcurrent here, as I said, in the DC line if the current is increasing. What you can do? We use the valve control. Very similar, we can use the valve control, and thereby we can reduce the voltage that is faster than your circuit breaker. So we use the here normally valve control to control here the overcurrent. Now another here, the two more protection systems are used once you use the damper circuit. Damper circuits basically used whenever there is a oscillation in the power. There is a, I'll discuss more detail later, maybe that's not today, it's the next lecture. So the damper circuits are used if there is a oscillations of the current in the DC link. There is a oscillations if in the AC system also happening. So we have to go for the damper circuit, and the damper circuit basically damp out those oscillations. So we'll find this damper circuit in the DC side we are using. Another we use the DC reactor. DC reactor basically controls your rate of rise of current, because this is a DC current. You know, we are not having here the, as I said, this is your converter station, this is your line. Here we don't have circuit breaker. If the current here is increasing, so to control the rate of rise of current, we use here smoothing reactors. No doubt that is giving you constant ripple is also reduced by this smoothing reactors, or you can say DC reactor, because it is a DC side. We also use reactors in the AC system, as explained in the very first lecture. We use the reactor for the purpose that different. In AC system, the reactors are used to control the voltage, and we use those reactors at basically the line to ground. So we use the line reactors, we use the bus reactor, we use tertiary reactors. All the reactors' purpose is to basically absorb the reactive powers in that one in the AC system. So those are the AC reactors. Here I am talking the DC reactors. Here the reactance L is used, but the purpose here to control the ripples in the DC side, so that we can have the constant DC current, and also it limits the rate of rise of current in the whenever there is a fault here, because if it is not there, huge current will be there. So we'll see the DC reactors and how the values are calculated to limit this current. Another problem other than this, we are having some other problems here. Like as DC system, we are having here AC as well. We are having the transformers, and then it is your bus here. We are having another side, so we are having the problems in the AC side. We are having the problem in the DC side, and we are having a problem inside the here as well. In AC system, we are having only problem this side, over voltage and over current. Now in the DC system, this line is exposed to the air, and there will be the lightning surges on this line. Also there is a problem here, the one bridge is not operating, the current will be also mismatching and the ground current will be there. So we require the differential protection, etc. We'll see later on. So here, so there is a possibility that you are having problem, the disturbance this side originated, and once it is originating this side, it will be reflected this side as well, because your thyristors are firing. So whatever the voltage rise here, it will come this side reflected. So that's why here I have written a disturbances originated on the AC side, here are the rectifier side, and similar it happens to the inverter side. So it will be coming reflected in the DC side, and thereby the disturbance will be there. So if the huge voltage is here, what happens? This voltage will be transmitted to this side through the transformer, and finally it is reflected here. If there is some problem here, this will be the inductance, again this will be coming here. So second one here, the disturbance originating on the DC side. Means let's suppose there is some problem here, pole to ground fault is there. This disturbance is here, but again it is coming through here and it is reflected this side. So this is going to create a problem in this your converter circuit. And due to the internal faults inside the converter itself, means there is a misfire, there is your a communication failure, it may be the arc through, a backfire, all the things happens inside here also, that is also the disturbance. means we are having the different currents here, we are having the different voltages, and those are also reflected in your AC side. So in whole DC system, I can say now we have this problem this side, problem this side, again here the problem is this side, and then we should have the protection scheme for all these three differently so that we can protect it and we can operate our HVDC system satisfactorily. Now we can categorize the disturbance into two categories. One is the external, another is internal. External means it is coming from outside, so it is external. So you can see the external, basically here we are having in the AC side we are having only external, and that is reflecting in the DC side. So here I can say the switching over voltage. Now you can see the time range. We are having the over voltage, very fast over voltage due to the here lightning strokes. You can see it is 0.3 to 3 millisecond due to the step rise and the decrease here. So this lightning over voltage is there. We are having the switching surges, means whenever you are opening and closing the circuit breaker, there the surges rises, and that is reflecting and it's flowing in the whole AC system, and that is also coming in the DC side as well. And this wave front is more than 10 milliseconds. Another is called the temporary overvoltage, or also called the dynamic overvoltage. The dynamic overvoltage here, basically it is lasting for a few seconds due to the load rejection in the weak AC system. Means to understand these overvoltages, you can see here this is your system, this is your load, and you are having a system which is feeding power here. Now to have the overvoltage here, one is coming here, that is a lightning stroke, and that is due to this overvoltage will be arises here because huge energy kiloampere is coming and it is flowing here, and that current multiplied by impedance will be added over that, and that voltage will go very high, but it's a very short duration. Another is here that you are having some fault here, then the voltage here experience here will be rise and it will be different voltage, transient voltage will be there. So it is called the switching over voltage because there is some fault or due to some switches here opening and closing. Another is your load rejection here. If the load is thrown off suddenly, it was operating the system very successfully, and here load is 0. Again there is a voltage will be there and it will be oscillating dynamic over voltage, that is called temporary over voltage or dynamic over voltages. So we have the different time scale. This is very fast, then the switching, then you are having here the load rejection, and that is called your dynamic over voltage or temporary over voltage, and it lasts for here the longer period for few seconds. Basically I can tell you with these three conditions, this normally we do go for all these studies, no doubt. This we go for this here the steep front over voltage lightning stroke. This basically we do this analysis, we go for the study for this type of over voltage, and that will be used for deciding your lightning arrestor rating, because it basically depends upon how much energy is going to come in the system that must be taken by the lightning arrestor. So because there is a kiloampere current is falling here, and that is huge energy is there, and that energy is basically rating of this. It is at rated voltage here, and then it's normal voltage, transient over voltage, and then the energy rating of this. So this we analyze our system for the lightning stroke to design the characteristic or rating of this lightning arrestors. This switching over voltage normally we also perform here, and we'll see our system stability concerns, whether your system is stable or not. Based on that we go for the fault clearing, how much it is duration it is there, your system will be stable or not. This voltage will be also higher, and we go for up to certain millisecond. Another here we go for the temporary over voltage. Basically that is a deciding factor of here the rating of your reactors, that is the line reactors or bus reactors, because that will control your this voltage here, because it will be during this over voltage more reactive power and voltage will be reduced here, more reactive power it will be absorbed by the inductor. So this will give your lightning arrestor decision, this will give your reactors rating. This gives your system stability and the concern, and also sometimes this will be used to decide the insulation of the system, because this 10 millisecond is more than enough sufficient to break down the insulation. This is not very small here, and it will be the insulation is not very much affected, very narrow time. This is the voltage is less, so insulation is also not affected. So insulation coordination and insulation reactor is decided, and the stability concern is basically analyzed by these. So these are the three broader criteria for the overvoltage analysis. The disturbance, which is the DC side, here as I said, now AC side the overvoltage will be only due to the faults, switching, and also due to the load rejection and so on and so forth, and then we can have some lightning stroke this side. So this will be arising. In the DC side, now we are coming here, external will be the again the some lightning surges coming on the DC tower, and once it is energy is coming, it should go in the both direction. Another here the switching surges due to the ground fault on the one pole produces the overvoltage on the unfaulted pole. Means if the fault is here and we are having two poles, this voltage here will be the different, and it will give the rate of rise overvoltage in this pole. One here is your lightning one, second one is due to the fault. So two here are basically, this is external because it's coming here. This is basically internal because due to the line to ground fault here inside the system. So overvoltage can also arise from the current and voltage oscillations caused by sudden jumps in the converter voltage due to the converter faults and the commutation failure. You know, we saw the commutation failure, we also saw the converter faults, all this misfire, arc through, back through, arc quenching, etc. In all this there is a sudden jumps, and sudden jumps are there. There are inductors, and there are some capacitance are formed even the ground to the high pole, and that will be there is some oscillations, and that will give you some rate of rise or some overvoltage will arise in the current as well as in the voltage. Switching of the DC filters, because we use the DC filters this side, we also use the DC filter across, we will see that will also give some overvoltage. The switching surges originating from the AC side transmitted to the DC side is also the concern, because the overvoltage here you are protecting no doubt, but during that period it is traveled this side, and since it is very fast here, it will be coming this side as well. So this side also overvoltage is going to occur, and whatever the voltage is going to transmit here. So that is one concern. So series connection of the valves group multiplies the overvoltage by the number of groups. I mean to say that here, let's suppose you are having various here bridges, all these here, even the voltage here there groups, this is going to be here, number of it is going to be added. This is the bus. If the voltage is here increased, what will happen? This voltage is going to added, this voltage is going to added, and this voltage for DC here is going to be multiplied. If the voltage here is increased by 1.05, let's suppose the voltage has gone, now here it is 1.15, because this voltage here, this is going to be added. These are in the series connections. So that's why it is said that the overvoltage, it will be the number of groups, means here in the commutation group 1 base here, that is going to be added, and therefore here that is a more serious concern, that is if you are using number of bridges more. Sudden loss of load in the rectifier circuit. Let's suppose there is some problem, this is a trip, and the sudden loss is 0 in the inverter side. If here the loss is there, the current will be made 0 at that time, sudden, because otherwise what will happen? The voltage will keep on reducing. As I said here, we maintain the current here constant, but if the suddenly this is your load is thrown off inverter side, what will happen? This will be your power is 0, voltage is same, current should be 0. Then the converter will try, because it will try to maintain the current and try to reduce the voltage, so that finally the power will be 0. So whenever the sudden load throw off, what happens? The voltage here, this voltage that is going to be dropped in a commutation circuit, this RCID, this voltage is going to be increased, because this was the voltage which was, this is included here. So this minus this voltage was there, and this voltage ID is 0, so voltage is going to be right. So there is some rise here in the sudden loss, but this is very less because this value is less, this is less, so it is not more than 7-8%, I can say. So this is not a big concern. Now increase overshoot of the DC voltage of bridges at the end of each commutation due to the short overlap. If overlap is short, what happens? The voltage rise, the dV by dt is very high, and due to this dV by dt, the voltage here can also be increased. So this is basically at the commutation. If the your current is suddenly changing, means your U is less, means the time duration of the takeover of current is very less. So sudden change, again the voltage will be going to rise, and this is the concern of this. Another over voltages and other transients in the DC system, whenever you are energizing your DC line, means you are slowly you are building it, energizing this. At that time you can see the voltages wave shape is not in the proper order, means it is not a symmetrical output to the DC side, and AC side currents are also sometimes just DC short circuit, means AC side there is a short circuit, and also this side the voltage is not uniform, and if there is short circuit, other phase voltage may increase. So energization can be also one concern. Another, due to the stray capacitance and the inductances, and due to the DC side here, and there is your voltage wave shapes and currents are changing suddenly here and there. So due to this, voltage rise will be there. So this is also a concern, and converter fault already I have discussed. So in total I can say here, for the over voltage we have to reduce it. Overcurrent is not a big concern because we are controlling here the converters here. The converters here, the valve control, we are only controlling the current by the valve. So we can hit it very fast, it is even the faster than your circuit breaker, and it will take care of the current to maintain this. But the rate of rise sometimes it is very high, then we have to have some protection for this, and we have here the DC reactors for that. So major concern here in HVDC system is the over voltage, and that's why we should have the various, here you can see now we are having the lightning arresters, or we should have the surge diverters are used. Surge diverters and your lightning arresters are same, because these surges are not going to the system, it is coming down to this your ground. Then we use plane gaps, we use in the DC lines the gaps here, and then we can use the ground wire on the top of the conductors to protect the over voltage due to the lightning strokes. Here these two protections are used. This is also for same. This is basically the primary here, and the secondary we use is for precise control the lightning arresters. But there is some problem here than the DC lightning arresters, because AC lightning arresters are very clear, because you know the current is also going to be 0 one cycle, but DC the current is DC. So the deionization process is difficult here in your DC. AC it is possible. Another, we control the over voltage by your converter control system, because if the over voltage is there this side, you can control the voltages here as well, and very well you can control. Then we can use the damping circuits if there is oscillation in the voltage over this oscillating voltage, so we can use the damper circuits. In the DC side normally we use the DC dampers, and we can use the DC reactor here to limit the rate of rise of current here. And then we can use sometimes surge capacitors. If there is some surges, the capacitor voltage will increase. It will basically, the surge capacitors are some sort of storing the energy devices. So if it is very huge energy there, it will store, but some voltage will rise, and then it can be released through the resistance or another circuits, and finally we can safeguard our system. So this is the over voltage protection scheme. You can see here what we have here. You can see we have the, this is a bipolar arrangement. We are having one pole here, and we are having one pole here, and this is your ground. You can see it simply. This is a grounded. Now we are having the, in this scheme you can see this is a bridge 1, bridge 2, means 2 bridge per pole we are having. In the another pole here, this is this, and this is this we are having. Now this is your, you can see the DC reactor arresters are we are using. This is a reactor basically. The reactor should also be protected, because if there is a huge current rises there, huge voltage will be induced across this reactor, and if it is very high, this coil will be burnt, insulator will burn. So we should have here, if the voltage is there, so what is this is a nonlinear resistance, it will try to provide the path. So we should also protect the reactor, because reactor is looking simple winding, but it is not so. It is very huge and very big, kiloampere current is flowing through this. And if the rate of rise of current in the DC is very high, then the huge voltage will be produced here, and then if the voltage is there, then what will happen? This will bypass it. So this is a resistor circuit, basically nonlinear. So some energy is dissipated here, and finally the voltage will be reduced. So we are having this DC reactor as well. This DC reactor is basically, I will discuss later on, that is used for the ripple control, it is used for the rate of rise also, and the values are decided accordingly. We are having here the DC line arresters. If there is any problem in the DC line here, what happens? Let's suppose there is some here lighting stroke is there, then it will be here, it will provide the ground path to that, and it should not go to our converter station. We should protect it, otherwise what will happen? Your converter circuit will be damaged, and then you have to shut off your HVDC link. So we provide here, means before this, even though smoothing reactor, and after also you can say here we are having the DC bus reactor, because this reactor is also exposed to air, it is outside, it is not inside. But this converter circuit, most of the time it is inside the building. So there is no possibility here falling there is no possibility of falling the lightning stroke. Only this reactor, so that's why from both sides of the reactor we are having this value. So this is you can again provide the ground path if it is happening this side of your DC reactor, and it will be grounded and energy will be released, and then it should not pass through this side. We are having, you can say, converter unit here arresters. This will be basically limiting if the voltage across here, I think I should explain here. We are having across this complete pole here, if due to certain problem, if the voltage here is rising, as I said, if the voltage is increased this side, it is passing through this converter circuit, and it is going to be multiplied by number of bridges. So here, even though there is 0.5% increase here, the 10% increase is going to be there, because due to the 255% here finally. So then if the voltage is exceeding its rating, now it is suppose 500 plus minus 500 kilovolt, if it is exceeding very high, then this will provide a path here. Otherwise what will happen? The huge voltage will be appearing across this, even though outgoing valves, and that may also damage this your converter circuit. So this we require the converter unit arresters, we call it, means this is a converter circuit here.
You may have another one on the downside also, same.
No, yeah, similar, we are having this side also. Then we are having, you can see this is your valve, we are having another here, and that is called your valve arrestor. Means individual valves are protected. If this voltage with this, and this voltage, this is with the ground, we are having, so this is a valve arresters. So we are also having, if the voltage here individually exceeding, then it will be providing the safeguard to this. And the arrestor, simply it is providing the ground path, and some energy will be released. So we are having the various here, your valve arresters, then we are having converter unit arresters, and thereby we are having sometimes midpoint also here the DC bus arresters. Now here, another here you can see we are having the neutral arresters, because the current which is going here, so if there is some voltage on other neutral here itself, then it will be here, that is also going to be there. This side is AC side, this is the converter transformers, you can say this is your 12 pulse and this is 12 pulse. I think we are having what is a monopolar operation basically, yes, because this is a 12 pulse, this is 12 pulse, and these bridges are added in series, so it is a 12 here. So this is monopolar operation, that's why it is neutral is coming here. So you can see here also we are having the AC bus here arresters, again it is a lighting arresters. If there is some problem in the transformer this side, then it will be providing ground path. Here we are having this AC reactor arresters. The reactor arresters means here we are using the reactors as well as the arresters. Here we use the reactors for what? This is basically nothing but this is related with the filters. We provide the reactors at the substation so that we can have the some harmonics current due to the capacitor, and here it can be flown down. So this reactor is also protected. Here this capacitor and inductors are there, we also have it here. So we have the lot of protection schemes so that we don't want that any of the here individual components should fail. and if any of the component will fail due to the overvoltage, we have to simply replace, we have to shut off this line and finally go for the replacement here. Here we can have, you can see the DC here, the filter resistor. We use the DC filters, as I said. We are having the AC filters, we are having the DC filters also to smooth the current here in this one, and this filter is there. So in this filter you are having the combination of inductor and your capacitors, and then we use again here the arrestors, because the voltage here can increase, and then because there is some more current will be flowing here, and then the voltage will rise here, and then it will take care. So we are having this, you can see for over voltage we are having lot of things to protect the whole our system. Now this is all about your over voltage. Let us go to your overcurrent protection, but before, here see the DC line arrestors. What is the difference between the AC line arrestor and DC line arrestor? The major concern here in the DC arrestor, here we don't have any natural zero. In AC always you are having a natural zero, and what happens, you are getting some zero somewhere, and then it can deionize your whatever the ionized path. But here we don't have a natural zero to aid the releasing of arrestor against the sustained DC voltage. If the voltage is increasing the DC voltage, so we don't have anything that it can switch off automatically. So what we do, we go for a special arrangement to provide some oscillating current in this here arrestor, so that we can get some natural. What happens? It is always possible. Let's suppose you are having a here the your DC current, DC here, this is your arrestor. Let's suppose you are having, we can add some here voltage with some circuit, that here current which is, if it is oscillating here and the DC it is added, then we can have the zero somewhere here crossing. Once zero crossing is there, then we have to deionize it, because the zero, and this is the big problem in the DC circuit breaker also, because the no zero, so the arc quenching, it is very difficult. We cannot arc quench it. Once it is an ionized path, it will be continuous ionization. So we make a special arrangement to make it zero somewhere, current also that. So in DC, if you are adding here, so you will get somewhere zero. Voltage here is buffered by the huge lamp reactors through the smoothing reactor and the transformer, which is not case of in the AC system. I mean to say that here your converter circuit is there. Here this inductor is the lump inductor. In the AC line, the inductance which is there, it is a distributed. So whenever it is falling, let's suppose here, or it is falling here, then it is falling here, but this value is only if it is a inductance falling here, means stroke. If a stroke is falling here, in this one, it is not causing any problem, means here the voltage is very high. But in the line here, which is AC lines, the inductance is the distributed. Here we are having the lumped inductances. This is the different than AC system. Also, if there is a here the transformer, this inductance is also just like a lumped inductance. So if there is some voltage here there, what is limited to this portion, and then it is injecting this. So in the DC line reactors, we consider these two concepts and we modify it so that it can be taken care and similar to the AC system. So here we try to provide the natural zero. Here we try that the inductance here, the rate of rise should be such that limited, so that we should not face any problem. So that's why here special lightning arrestors are built for the DC lines with some modifications. But again the purpose is same. Now coming to your protection against overcurrent. The main feature of converter protection is that it possibility to clear fault by the fast controller action less than 20 millisecond. Means you can see why I am saying the 20 millisecond. If it is a 50 hertz cycle, then one cycle or some of the faults are automatically cleared. We cite commutation failure, it is self clearing. Misfire is also self clearing. All the faults are almost self clearing. One cycle, if there is no persistent problem, then after one cycle it will go off. So if it is persisting, then we have to have some protection scheme to control the overcurrent as well. Differential protection is used because it is a selective and the fast detection. The differential protection are basically used for that is called the unit protection. It is used for your normally any apparatus, like used for transformer, it is used for generator binding, Sometimes earlier it was used for the transmission lines also, but it is not used because you require the pilot wire for this. But if your operator is very small, we can use the differential protection. Here also in HVDC we use the differential protection if the currents in the two poles are different or there is some faults in the AC side. Overcurrent protection is used as a backup always. If the current is exceeding somewhere, then we can use the overcurrent protection. I'll show you where these protection schemes are applied. The level of overcurrent required to trip must be set higher than that of valve group differential protection. The pole differential protection is used to detect the ground fault. If there is, let's suppose here the fault is there, then we have to see that here there will be current, and in other here pole the current will be not there, then we have to go for the differential protection. You see this is a schematic diagram for this current protection. You can see this, we are having here the smoothing reactor here. We are measuring the current here by the CT. Now you can see if it is a DC current, the CT will be 0, the current, because it is only the transformer works in the your AC. But I mean to say that we can measure even the DC current with some other measuring instruments. It is not a CT here, but it is, we can use the Hall effect, we can use some other devices, based on that the field etc. we can measure the current, what is the current flowing. Means we have the DC instruments that can measure the current, and that can be transformed in the different fashion. So we require the measuring of the current here. So it is shown as a CT, but it is not CT, because CT is only used in the AC systems. So we are measuring the current here. You can say we are having here the pole differential protection. If there is some current mismatch here, then there will be some difference and this relay will operate. Means if the current will flow here, if both current here coming here is the same, then induced voltage here and here will be the same and there will be no current here. Then relay will not operate. But if there is some mismatch in the pole currents here, then it will operate, and then we have to, it will give the signal first. If there is a small value of the difference is there, then it will indicate. If it large, then it will trip it will give the trip command to somewhere here, then circuit breaker. Now you can see we have the valve group protection here, that we are also measuring the current here and this current here, and the difference is taken here. We are using this group, valve group here. This is one valve, it is another valve here, the bridge we are talking. So this is the basically current difference here. No doubt the current here, the AC side we are talking, here is the DC side we are talking. But here we are taking the value, there is some factor we are using, so that this current and this current should have the synchronized one. And if there is some mismatch based on that, then they should operate this value. So this is overcurrent here. Now another we are using here the simple overcurrent protection scheme. If this current is exceeding high, let's suppose there is a fault here, that's our circuit, then the current will be more and this will trip it here. Similarly, we are having overcurrent protection scheme here of this transformer. So in all this here you can see what is happening. This thing will be giving command to here bus, AC bus here. This is the system will be isolated. If again, what is your fault level? How much high values we are going to put? So that's why it is your overcurrent protection scheme. Earlier I showed you this overvoltage protection scheme of this DC circuit, HVDC link basically. Now one thing is here is very important, that is the DC reactor, and normally this reactor value you can see it is in Henry. It is 0.1 H to 1 H Henry, it is basically required this reactor, and this reactor is basically is a limiting value of a fault occurring here. It is also used to control the ripple, but it is more important if there is some fault here, and if this inductance is not there, what will happen, this voltage divided by the impedance, this R and the impedance of the line, it is very high value current will be there. But if due to this inductance there is a fault here, current is going to increase, and thereby this is trying to introduce the voltage. This voltage minus this voltage is going to appear here. So its current is very fast, this voltage is very high. So it is trying to reduce the voltage here and trying to limit rate of rise of current, and once it is limiting current is rising, meanwhile your converter circuit will take care and it will try to reduce the current. So this inductance is basically, you can say, it limits di by dt here rise to prevent the commutation failure in the inverter of one of the bridge when the DC voltage of one bridge collapses. Because here one option that there is a fault, another also there is a possibility the problem in the inverter side. If inverter side here the voltage has gone down, the current will exceed. And you know, if the inverter side voltage has gone down, current is exceeding, now what will happen? The commutation failure is one of the big concern. So this inductance basically is decided that it should, the value of LD is calculated so that it can prevent the commutation failure. Means it will try the firing angle and your minimum angle is given, then how much U it is exceeding so that commutation failure can be avoided. We will see how to calculate this value. It reduces the incidence of commutation failure in inverter due to the AC dip, no doubt. It reduces the harmonic voltage and the current in the DC link. As I said, it can, the DC voltage here, this whatever the ripple is there, so it is working as a smoothing reactor, that's why it is sometimes known as. So the current here is almost constant, is made by this ripple is reduced. It reduces the current ripples, the DC current is almost maintains constant, the voltage also is reduced, harmonic voltage, and it also limits the crest of the short circuit current in the DC line when it is a fault. So when there is a fault, it is limiting the fault current. If the inverter side voltage is reduced, then it is trying to reduce, basically it is nothing but di by dt control, and that is a very useful, this inductor. To see this here, we can calculate what will be the inductance value for the sufficiently limiting the rise of DC current after the collapse on the DC side voltage. Then based on the various assumptions, in the next lecture we will see how this LD will be, what will be the suitable value of LD for the inverter side. In that assumptions we will see your DC voltage is, it is assumed that a constant when the collapse has occurred before that instant. The AC voltage or inverter here becomes same, which is a constant we are talking. The tap changer is not operating, otherwise tap changer will also control, action will operate. The initial current was ID normal current, and then the collapse of the voltage occurs simultaneously when the beginning of the commutation takes place. With these assumptions, basically we will try to calculate what will be the value of inductance of this smoothing reactor or DC reactor, so that we can limit the commutation failure, because the commutation failure here always we know that this is your, here the beta is the firing, and then we maintain here the gamma minimum. Beta is calculated even though at certain here it was the gamma here in the normal condition, but due to the U it will try to increase, and this value if it is exceeding here, then there is a possibility, this minimum is decided that if it is coming this side, the commutation possibility of commutation failure will be there. So we will see that this is a normal gamma, it was operating, the fired here, U was there this value, and it was, the thyristor was off, that valve was, commutation was successful, but due to certain problem as collapse of the voltage, this may exceed here and finally come in this side, and the commutation failure may occur. So we will calculate based on this criteria what will be the value of LD in the next lecture. So the next lecture will be the end of this module lecture, and that will be next term. Thank you.